Pre-Calc BC, today we are going to start talking about limits involving infinity. And before we begin, just a quick end behavior asymptote recap from what we did first semester. So when we talked about end behavior asymptotes, there were three different situations, and it was based on what degree was bigger where. So if the degree was bigger in the denominator, for example, y equals 3x over 5x squared, we said there was a horizontal asymptote of y equals 0. If your degree was equal in the numerator and in the denominator, for example, y equals 2x squared over 4x squared, then we said that we took the ratio of the lead coefficients. So in this situation, our horizontal asymptote would be at y equals 1/2, 2 over 4. If the degree was bigger in the numerator, then we had some other sort of end behavior asymptote, whether it was a linear asymptote, which was called oblique, or maybe it was parabolic, or maybe it was cubic. In any case, we had to do long division. All right, so we'll be coming back to those ideas in a little bit, but for right now, let's move on to drawing a sketch of f of x equals 1 over x, and we're going to determine these infinite limits. The limit as x approaches infinity of 1 over x, and the limit as x approaches negative infinity of 1 over x. So we should be familiar with 1 over x being the reciprocal function, which should look like this, and you can go ahead and graph that if you need to. Okay, so this has actually a horizontal asymptote at y equals 0. Okay, it technically has a vertical asymptote at x equals 0 as well, but we're going to get to vertical asymptotes in a little bit. So we can identify that from this picture, but let's actually get a definition of how we know if we have horizontal asymptote using limits. So a horizontal asymptote is the line y equals b. And we're going to say is a horizontal asymptote if and only if either, okay, so either of these situations, the limit as x approaches 0, or excuse me, x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b. What this means is that technically we can have two horizontal asymptotes, okay? If we have the limit as x approaching infinity and the limit as x approaches negative infinity to be two different values, we can have two horizontal asymptotes. We cannot have more than that, okay? So if you take a look, as we approach infinity, we are approaching 0. Oops, I keep wanting to put a 0. As we approach infinity, as x approaches infinity, our limit is 0. And as x approaches negative infinity, so that's going to the left, we are also approaching 0. See how we get 0 for both of them? That means there's only one horizontal asymptote, and that horizontal asymptote is y equals 0. Okay, so that's how horizontal asymptotes relate to limits. Okay, let's try another one. Use your calculator to determine the following. Identify any horizontal asymptotes. Draw a sketch to justify your answer. I've gone ahead and I've typed this equation into my calculator and I have graphed it. Okay, and we can draw a quick sketch of this. So we have 2 and negative 2. All right, so let's take a look. The limit as x approaches infinity of this function, so x approaches infinity, we're approaching, infinity would be all the way to the right. So it's up at 2. And as x approaches negative infinity, that means we're going all the way to the left, and we're down at negative 2. So this actually has two horizontal asymptotes. It has one at y equals 2, and it has one at y equals negative 2. And again, the most you can have is two horizontal asymptotes because it's what's happening as x approaches infinity and as x is approaching negative infinity. Those are the only two options. All right, so let's use limit properties to find the following limits without a calculator and determine any horizontal asymptotes. Now, some people might be able to just think of this visually. This is the reciprocal function that's just been moved up 2. Okay, so you may be like, oh, well, I know what the limit is automatically, but that's all right. Let's go ahead and use our limit properties just to confirm. So the first thing I'm going to do is I'm just going to start with x approaches infinity. A lot of times it turns out to be the same thing when x approaches negative infinity. We'll see in just a minute. And I'm going to split my limit. So I'm going to do limit as x approaches infinity of 2 plus limit as x approaches infinity of 1 over x. Okay, well, this is just 2 because it doesn't matter what x is. This is still a value of 2. Think of it as a horizontal line. And what we just showed was that x approaches infinity of 1 over x. That is a 0. So 2 plus 0 is 2. All right, and now we'll go ahead and we'll do it with limit as x approaches negative infinity. And then again, I'm going to split my limit here. And again, this is not going to be a difference. It's just going to be a 2. And we also found that as the limit as x approaches negative infinity of 1 over x is also a 0. And so again, this is just a 2. And since we get the same thing for both, we determine that there's only one horizontal asymptote, and that is at y equals 2. Okay, and again, that makes sense because we're taking the reciprocal function, we're basically shifting it up 2. So since our horizontal asymptote was at y equals 0 before, now it makes sense it would be at y equals 2. Now, let's do the limit as x approaches plus or minus infinity of sine x over x. So sine x over x, we knew the limit for this as x approaches 0, it was 1, but this is the limit as x approaches positive or negative infinity. Now you may remember from the graph, so you might have an idea of what the limit is, but we're going to use the sandwich theorem to confirm this. So sandwich theorem, I'm going to start with my sine x, and I'm going to put that between -1 and 1. And then how do I get sine x over x? Well, I would just multiply all of this by 1 over x. So again, the way sandwich theorem works is that if you can show that the limit of these two guys here are the same, since sine of x over x is right in between these two functions, we can also identify the limit of sine x over x. So I'm going to do limit as x approaches infinity of -1 over x, and the limit as x approaches infinity of positive 1 over x. Whoops, there shouldn't be an equal sign there. So 1 over x we know is just the reciprocal function, and that is just 0. Okay, the other reason you know is it has to do with your end behavior asymptotes. Your degree is on the bottom, or your degree is bigger on the bottom, and so that's always a horizontal asymptote of y equals 0. So 2 ways you can think of it, just from visually the graph or from knowing about your end behavior asymptotes. -1 over x is just the reciprocal function, but it is reflected over the x-axis. So this is still going to be a 0. That doesn't change. Again, you can also say degree is bigger in the bottom. So that's 0 for both. All right, so therefore, the limit of sine x over x as x approaches infinity is also going to be equal to 0. And you can see if I change this to a negative infinity, it's not going to change, right? It's still going to be true as x approaches negative infinity. So we have a new identity that we know. As x approaches positive or negative infinity, sine x over x has a limit of 0. And as x approaches 0, sine over x has a limit of 1. So that was something that we knew before. Okay, so 2 things that we can use. All right, so now number 4 and 5 are really the same type of problem, but we are going to do this in 2 different ways. First, we're going to use limit properties, and then we're going to use sandwich theorem. Okay, we'll see what you prefer. So limit properties, I'm going to go ahead and I'm going to split my fraction. That's just some algebra. 5x over x plus sine x over x. Then I'm going to split my limit. Okay, so that's where they each get their own limit. And oh, we should have parentheses around that. Okay, sine x over x. Okay, so now we can also simplify this, right? So your x's are going to cancel. So this is really just the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over x. Okay, so now these are two separate limits. We can identify them or calculate them separately. The limit as x approaches infinity of 5, well, that's just a 5. And this is our identity that we just did. This is going to be a 0. And we are adding them together, so 5 plus 0 is 5. Equals 5. All right, so now let's do this with sandwich theorem. Sandwich theorem, you're going to start off with just your sine x. And we know that's between 1 and negative 1. So now think, how would you construct this function here? Well, the first thing you have to do is to add the 5x to everything. So that's going to be 5x minus 1 less than or equal to 5x plus sine x less than or equal to 5x plus 1. And then we're going to multiply everything by 1 over x. And that should construct the function that we want it to be. Which I believe it is. Yep, 5x plus sine x over x. So this is the guy we want. And so now we're going to find the limit of each of the kind of like end functions. And if those are the same, then we can identify the limit of 5x plus sine of x over x. Okay, so limit as x approaches infinity of this. Okay, and again, you want to show this step by step. So if you want to split your fraction and split your limit at the same time, you can. So like I can say this is limit as x approaches infinity of 5x over x minus the limit as x approaches infinity of 1 over x. You could also make it a plus, and then it's the limit of negative 1 over x. It doesn't really matter. They're the same thing, right? So now my x's will cancel. So I have 5 minus the limit as x approaches infinity of 1 over x. And we can go ahead and calculate each of these. The limit as x approaches infinity of 5 is 5 minus the limit as x approaches infinity of 1 over x is 0. And that gives us 5. Okay. Now we do have to do this again with 5x plus 1 over x. So yes, this does take a little longer. And I have run out of room, so I'm going to come over here. So it's the same thing just with the plus. All right, so again, we can split our limit and our fraction. 5x over x plus the limit as x approaches infinity of 1 over x. X's cancel. And we can see we're going to get the exact same thing. This is still a 5 plus, this is still a 0. So we're going to get a 5 for both. But when you do the sandwich theorem, you are going to have to confirm that you got the same thing. So somewhere we're going to say, therefore, the limit as x approaches infinity of 5x plus sine x over x equals 5. And there you go. All right, so now let's talk more about end behavior models. how the graph behaves as it approaches plus or minus infinity. That is what we're really talking about with an end behavior model. Now, before we called them an end behavior asymptote, that was a specific equation. We are going to be more general here. We more care about the model is kind of giving us a general idea of what the graph is doing. It's not a specific equation. So this is used to help determine whether the limit is plus or minus infinity. Okay, and this has to do with our degrees that we talked about at the beginning. So when you have an infinite limit, if x is approaching infinity or negative infinity, that tells us we are dealing with an end behavior model. Okay, an end behavior model. So end behavior models, when you have a polynomial function, we are looking at degree. So I take a look, this is a polynomial function. I have a bigger degree on the top than on the bottom. So in the past, what we did was we did long division. You are not going to have to do long division. You are just going to divide the lead degrees for both the top and the bottom. So your end behavior model in this situation would be y equals 2x squared. Okay, so what does that mean? That means that at the ends of your graph, this equation is going to follow an asymptote that looks something like this. It's a parabola and it's facing up. So what we're going to do is we're going to use that to tell us what the limit is. We don't need to know exactly what the equation is. If it's 2x squared plus 3x plus 5, something like that. That's what we did when we divided. We did long division in the past. I just need to know like which direction is this going and what shape is it in. So that's why dividing just the first terms is sufficient for what we are doing. So now I want as x approaches infinity. That means all the way to the right. As I go all the way to the right, what's this doing? It's going up. So the limit is positive infinity. All right, what about as I approach negative infinity? That means I'm going to the left. What's the graph doing? Well, it's going up. That means that my limit as x approaches negative infinity is also positive infinity. It's infinity for both because the graph of the parabola is going up from as we approach both infinity and negative infinity. So this is up, up. Okay, so now let's try it again. Polynomial function, infinite limit. Look at your degrees. Degree is bigger on the bottom. That means we have a horizontal asymptote of y equals 0. The limit is just 0. Okay, and then let's try one more like this. Infinite limit, okay, we have 2x to the 5th over x squared. Limit is bigger on top, or excuse me, degree is bigger on top. Go ahead, divide. That's going to be a 2x cubed. That's going to be your end behavior model. That will look something like this. So as x approaches positive infinity, we are going up. This is asking as x approaches negative infinity. So to the left, we are going down. So that means my limit is negative infinity. All right, so let's make this a little more difficult. We still have an infinite limit. What's going to help is if you go ahead and you multiply these together, if you do the algebra before you worry about the limits. So I'm just going to come over here. I'm going to start by getting a common denominator for the first one. So I'm going to multiply by x plus 1 on top and bottom. Again, I'm not worrying about my limit notation yet because I'm not actually doing anything with limits. I'm just going to multiply these together. So I have this times this. Okay, so this is a 2x plus 2 minus x. So that's just going to be an x plus 2 over x plus 1 times an x squared over 3 plus x squared. All right, let's FOIL that out. That's going to be x cubed plus 2x squared on the top. And then on the bottom, I'm going to have x cubed plus x squared plus 3x plus 3. All right, so now let's rewrite it. We're finding the limit as x approaches infinity of this. So now when you look at this, it's a polynomial function. The degrees are equal on top and bottom. So now we can go ahead and we can divide the ratio of the lead coefficients, which is a 1 over a 1. That means we have a horizontal asymptote at y equals 1, which means that is our limit. It is 1. Okay, so basically you have two options. You either have, when you have an infinite limit, you either have a horizontal asymptote, and the value of the horizontal asymptote is the limit, or your degree is bigger on top, and you have to divide, figure out what shape it is, and then look at infinity or negative infinity and see which way your arrow is going, and you'll either have a positive infinity or a negative infinity for your limit. All right, just a few more things to talk about. First, we're going to find the right and left-hand behavior models for this guy right here. This is a little weird. Right end behavior model, left end behavior model. Usually when we have these types of problems, we have something weird with an exponential, something like that. And essentially, right end behavior model, we are going to plug an infinity in for x. And left end behavior model, we're going to plug a negative infinity in for x. And we're basically going to see which part of the equation influences the graph more. So let's take a look. X is becoming infinity. X is becoming infinity. Okay, well, infinity, obviously that's really big. E to the negative infinity, this is really 1 over e to the infinity. So this is 1 divided by like a really big number. 1 divided by a really big number, this is essentially becoming 0. So this guy's bigger, this guy wins out. He wins. So that was related to the x. So your right end behavior model is just y equals x. Okay, so now we're going to do the same thing. You plug in a negative infinity for x. This is already negative, so this becomes a positive infinity. So like obviously negative infinity, that's like a really big value in the negatives. E to the infinity though, that's exponential. That's going to get bigger a lot faster. So this guy wins. He's like overtaking the equation. And so that would be y equals e to the negative x. That would be our left end behavior model. So what that's telling you is on the right side of your equation, as x approaches infinity, your graph is going to be following the line y equals x. And on the left side of your equation, your graph is going to be following this guy right here. That for you really quickly. So again, here's the original equation. So again, we can see on the right side, right end behavior model, this is basically like the line y equals x. I can plug that in there. Okay, and on the left side, it's going to be following e to the negative x, which if I can type it in. All right, so there you go. Last thing we're going to talk about are infinite limits as x approaches a. So this has to do with vertical asymptotes. F of x equals 1 over x. Again, we already said that has a horizontal asymptote, but it has a vertical asymptote as well. Okay, so there's that reciprocal function. As x approaches 0 from the right, okay, so again, this should be familiar from intermediate behavior. Approaching 0 from the right, this guy's going up. This is a positive infinity. As x approaches 0 from the left, this is going down. This is a negative infinity. Okay, so those are your limits. Let's talk about vertical asymptote as a definition of limits. We say that the line x equals a is a vertical asymptote if and only if either the limit as x approaches a from the right is equal to positive or negative infinity, or the limit as x approaches a from the left, oops, I forgot my f of x, is equal to positive or negative infinity. The important thing is that if you're approaching positive or negative infinity, as you approach a specific value from the left or the right, that means that you have a vertical asymptote. Okay, so we are approaching positive or negative infinity as we approach 0 from the left or the right, which tells us that x equals 0 is our vertical asymptote. All right, now we should be comfortable identifying vertical asymptotes based on our previous units of study. So what you should be able to see here is, oh, I have x minus 3 in the denominator. X equals 3 is a vertical asymptote. And I am approaching the vertical asymptote. Okay, I am approaching x equals 3. So if you're approaching a vertical asymptote, you either are going up or you are going down. Those are the only options, right? If you have a vertical asymptote, you're either approaching infinity or you're approaching negative infinity. You can't go through the vertical asymptote. So the goal here is just to determine what you are approaching, positive or negative infinity. So here's how you do that. Clearly you can't actually plug in a 3 because you're going to get a 0 in the denominator. So you're going to plug in something really, really close to 3. If you're approaching 3 from the right, something just to the right of 3 would be like a 3.1. Okay, you don't actually have to plug in the 3.1. Just think about what signs you would get. So 2 times 3.1 squared minus 3, that's going to be a positive. 3.1 minus 3, that's going to be a positive. A positive divided by a positive is a positive. So we are approaching positive infinity. Here we're approaching 3 from the left. So again, you can't plug in 3 because then you get a 0 in the denominator. But we're approaching it from the left, so think of something really close to 3 on the left would be like a 2.9. 2 times 2.9 squared minus 3, well, that's a positive. 2.9 minus 3, that's a negative. A positive divided by a negative is a negative. And again, it has to be infinity because you're approaching a vertical asymptote. You can only go up or down. You're just trying to determine the sign. The other reason you know these are going to be different is because of intermediate behavior. See how the degree of the vertical asymptote is an odd? That means what we know from intermediate behavior is that your direction is going to be opposite around your vertical asymptote. Whereas in number 12, an even degree for your vertical asymptote meant that you were going the same direction. Okay, so let's try that and see if it works. I have x plus 2. That should tell me negative 2 is a vertical asymptote. Okay, so I'm approaching negative 2. I'm approaching a vertical asymptote. That means my answer can only be positive infinity or negative infinity. I just have to figure out which it is. So negative 2 from the right, I want something to the right of negative 2. I'm going to do negative 1.9. Well, 1, that's a positive. Negative 1.9 plus 2 is a positive. Square it is a positive. Positive divided by positive is a positive infinity. Okay, now I'm going to do the same thing, but I'm doing negative 2 from the left. So this is like a negative 2.1. Here's the thing. Even though negative 2.1 plus 2 would be a negative, you're still squaring it, which makes it a positive. So this limit is positive infinity. Notice how they're both the same thing? Again, that's because of this even degree. All right, our last one, find the limit as x approaches 2 of this. Okay, so one thing that would be good to do is to factor. We can definitely factor the top. So it's going to be a minus 3, a plus 3, and a minus 2. The bottom doesn't look like it's too easy to factor right now. So one thing you could do is you could plug in the 2 and maybe we just get lucky and maybe we get a value. So if you plug in 2 on the top, you're going to get a 0, right? Because 2 minus 2 is 0. But maybe you don't get a 0 on the bottom. Let's see. So 2 cubed is 8 times 3 is 24 plus 4 times 5 is 20, minus, this is going to be a 46, plus 2. So this is 44 minus 46 is negative 2 plus 2. Okay, that's a 0 as well. So we get a 0 over 0. Okay, what does that mean? Well, it means that you had a 0 on the bottom, which means that you had to have had an x minus 2 on the bottom. Otherwise, you wouldn't have gotten a 0 when you plugged it in. So what we are going to do is we are going to factor the bottom by using synthetic division. I know that 2 should give me a 0, okay, because I plugged it in, it literally just gave me a 0. So I'm going to put 3, 5, negative 23, 2. I'm only doing the bottom because that's the only part I need help factoring. Multiply, add, multiply, add, multiply, add. We do get a 0. That's good. So now I can factor this. I have the limit as x approaches 2 of the top was this. The bottom, we know we have an x minus 2 because the 2 made us get a 0, which means 2 is a factor. And then I have 3x squared plus 11x minus 1. So here's the thing. The 2 actually isn't a vertical asymptote. It's a whole. Okay, they cancel. So once you cancel out that whole, we should be able to plug the 2 in. 2 plus 3 is 5. 2 squared is 4 times 3 is 12 plus 22 minus 1. And we should get that our limit is 5 over 33. All right, and there you go. I hope this was very informative, and I hope you have a great day. Bye.